For today's session, we are extremely delighted to have Saurabh Garg from Carnegie Mellon. So Saurabh is a fourth-year Ph.D. student in the machine learning department at CMU, advised by Zachary, Lipton, and Sivaraman, Balakrishnan. Saurabh is interested in building robust and deploying machine learning systems. The primary focus of his research is to improve and evaluate deep learning models in the face of distribution shifts. Before he started his PhD, Saurabh received his bachelor's degree from the Indian Institute of Technology, Bombay, majoring in computer science and engineering. I think at this point, I will stop sharing, and Saurabh, I think the stage is yours.
Great. Thanks for the introduction. So hi, I'm Saurabh Garg. Today I'll be talking about domain adaptation under relaxed label shift. So like just to give a TLDR of what to expect in the talk, I'll basically present some problems that sort of arise when label proportions shift from distribution 1 to distribution 2, and maybe some solutions on how we can start thinking about mitigating that problem. And in this work, we've introduced sort of a benchmark to sort of think about this problem and explore this problem experimentally. And we have released all the resources, and I'll have links to all of these towards the end of the talk. So let's get started. So we are right now in exciting times with machine learning, and we have seen sort of huge successes of deep learning, starting from the ImageNet movement that sort of led to interesting architectures like LXNet, ResNets, and things like that. And then more recently, we have started tackling problems which are of increasing difficulty. Like we have seen successes in AlphaFold, which is related to protein folding problem. And then more recently, sort of release of GPT-3 and ChatGPT and sort of image gen and like stable diffusion models. We are really in like exciting times of machine learning. And this has sparked interest in various applications, for example, medical domain, where people have seen sort of superhuman performance in like skin cancer detection. And sort of thinking about like diabetic retinopathy, people have seen sort of huge successes of machine learning in standard IID settings to see superhuman performance. However, this standard machine learning and deep learning are sort of a paradigm where we have IID holdout sets, where we train model on like some training distribution and we evaluate on some holdout set from the same training distribution, has a lot of successes. It fails when we start seeing distribution shift. That is when the deployment distribution or the distribution that my model sees during deployment is different from the training distribution. And this is due to various reasons where like models latch into like spurious correlations and things like that. And there have been like a lot of works trying to explore these deep learning solutions for like COVID detection. But there have been many reviews in like medical journals where people show that most of the machine learnings were not really even getting like performance better than baselines when they were trying to sort of deploy these models in like different settings from which they were sort of trained on or like evaluated on. Okay, so despite the success that we have seen, it's sort of fairly commonly sort of accepted that currently we don't have standard deep learning sort of doing good under distribution shift scenarios. And one of the common reasons that I think for this problem is like lack of rigor in benchmark-driven empirical research. Like, okay, people create sort of benchmarks that target like very general problems, and maybe we end up seeing sort of minimal to like no improvements on those benchmarks, or often the improvements are sort of very catered to those specific benchmarks. And yeah, like before sort of introducing like what are the issues with maybe some of the existing benchmarks and how we are thinking about this problem, let me talk about what are like different scenarios in which distribution shift problem can appear. So I've categorized them into like 3 broad categories. One is domain generalization. Other is transfer learning, when we have small amount of label data from target distribution. And the third is sort of domain adaptation problem. All of these settings differ in what data we have available during training and adaptation. So for example, the domain generalization problem, we have training data from multiple different source distributions on which we can sort of train. And the hope is that we'll generalize to a previously unseen target or like test distribution. In transfer learning, when we have sort of small amount of label data, we hope that we can train a big model on some source distribution where we may have a lot of label data. And then we hope to adapt that model with small amount of label data from the distribution of interest. And the third problem is like this domain adaptation problem, or like more commonly known as unsupervised domain adaptation, where we have access to labeled source data, like labeled data from a training distribution, and unlabeled data from test distribution. And the hope is that we can sort of transfer our model that we've trained on some source distribution to target distribution only with unlabeled data. Yeah, one thing that I would say here is please feel free to stop me at any point if there's any clarification question. We'll take like questions that maybe need more discussion towards the end. So, okay, so let me formally introduce the domain adaptation setup, which is mostly the focus of this talk. So here we have labeled data from source distribution and unlabeled data from target distribution, which can be different from source distribution. And the goal here is to perform well on test or target distribution without seeing any labels from that. So, okay. And in this talk, I'll mainly focus on distribution shift problems that arise due to sort of changing class prevalences. So we'll mostly tackle classification, in particular multi-class classification problems, where the source proportion of different classes can be different from target proportions of different classes, and how do they impact current machine learning models, and maybe how can we think about rectifying some of these issues. Let me introduce this problem with an archetype example of disease diagnosis. So let's say I have patient data, labeled patient data from hospital 1, which may include like chest X-ray images and the corresponding disease diagnosis. And let's say we train a deep model. In particular, we train for, let's say, K-way classification among diseases, pneumonia, tuberculosis, and asthma. And let's say these are the proportions, like the proportion that we see on slide for different diseases. Now, when we take this model and deploy this model in the wild, let's say on some hospital 2, the proportion of different diseases can be different due to differences in demographic or due to simply passage over time. And here, now we'll have IID violation. That is, the distribution of data in hospital 2 is now not the same as distribution of data in hospital 1. And then the natural question is, can we trust our model that we have trained and maybe evaluated on hospital 1 that will do good on hospital 2? And this is maybe the problem that I'll try to sort of answer in this talk, and maybe we'll touch upon an answer in this talk. Okay, so let's consider the simplest setup for this problem of label proportion shift, which is this label shift setting. So under this, we obtain sort of a well-posed setting. What do we mean by that? We mean by that when we have labeled source data and unlabeled target data, under some minor additional assumptions, we'll have sort of a unique solution. And what is this assumption? This assumption basically says that the label proportions Py can change from source to target, but the conditional P of X given Y doesn't change. Instantiating this in the problem that we were discussing before, what do we simply mean is given a disease, the distribution over symptoms don't change from hospital 1 to 2, but the prevalences of these diseases can themselves change. And under this setting, our goal is to estimate the target label marginal, which is this PT of Y, and adapt a classifier that is maybe trained on source data to target data. And note that this problem is non-trivial because we do not observe target labels. So we cannot do simple counting or training directly on target distribution. For this problem, there are many effective solutions that are applicable in like deep learning regime. However, when sort of this assumption that P of X given Y doesn't change breaks in practice, it's unclear how existing methods that tackle sort of label shift problem would respond. And in this work, we sort of take a step in relaxing this assumption that P of X given Y cannot change. and construct a benchmark that sort of takes in various different real world scenarios and introduces like this problem of like relaxed label shift to see how our current algorithms respond, and also probably thinking about how can we do method development in that setting. So motivation for this relaxed label shift is the following. Like, let's go back to like our archetype example where we had data from hospital 1, like labeled data from hospital 1 and unlabeled data from hospital 2. In practice, we have seen that from these different hospitals, not only that the class proportions can change, but because of differences in like imaging techniques that these different hospitals use, the density histograms for each class may also differ. So here we have simply plotted average densities across different classes among different clients. So client 1, client 2, client 3 are different hospitals. And we can see that both the label proportions for different diseases, which are denoted by the histogram in the bottom with different colors, the prevalences of these diseases change. And at the same time, due to differences in like these imaging techniques, the intensity histograms also differ. Okay, so let me introduce the setup a bit more formally. So we assume that the label proportions can change arbitrarily from source to target, but the distribution P of X given Y will vary in some comparatively restrictive way, in the sense that this restriction will be guided by sort of distributions that appear in the wild, like that appear in sort of real world scenarios. And our focus in this work is to sort of present like an empirical evaluation of existing techniques on real world problems. Okay, maybe I'll pause here for a minute if there's any question. Otherwise, I'll introduce our benchmark. Okay. So, and yeah, as before, our goal is to sort of evaluate and estimate like the target label marginal, which is like proportion of different classes, and also adapt a source to like, and also adapt source classifier to target data. Okay, so pictorially sort of representing this problem, we have like source domain and target domain, where the label proportions can differ a lot. And at the same time, the differences in P of X given Y are demonstrated in the right, where differences can arise due to differences in breeds. So for example, we can have like the same animal, but like different subclasses or subbreeds of those animals. For medical data, for sort of cell identification problem or tumor identification problem, we can have differences due to differences in like pigmentation techniques that people use. Or with respect to like this civil common data set, the differences in P of X given Y can arise due to differences in like group demographics and things like that. So these are sort of the data sets that we consider in our benchmark. And at the same time, we sort of simulate and we add sort of shifts in label proportions, which is denoted in the left. Before sort of discussing more into like our benchmark, let me quickly highlight problems with like existing work. So there are several benchmarks for domain adaptation problem. However, most of these academic benchmarks exhibit little to no shift in label distribution, in the sense that the label proportions that people have curated these benchmarks on have the label proportions are same in like source and target in these benchmarks. And they are also often because of being very careful in how they are curating these data sets. And consequently, we observe in our exploration that this benchmark-driven research has produced heuristics that implicitly assume that there is no class prior shift among source and target. And we'll demonstrate this failure in a couple of slides. On the other hand, problems that methods that sort of try to tackle this relaxed label shift problem have begun to sort of emerge very recently. However, it is difficult to assess the state of these different papers and like works because of inconsistency among how they are evaluating their methods, among what data sets they use in these different papers. And also like there are often missing baselines in these papers, and it's unclear how do they do model selection, in the sense that how do they tune their hyperparameters when we do not have access to target label data. Overall, we observe and we show that there is like fair and realistic comparison among different methods is sort of missing in recent literature for this specific problem of like relaxed label shift. And hence, to sort of start tackling this problem, we introduce our benchmark, which we call as RLS bench, towards to sort of enable like a more holistic evaluation of these domain adaptation problems where label proportions can also shift. So our benchmark consists of more than 500 distribution shift pairs, that is 500 different pairs of source and target distributions with varying severity in class proportion shifts and target across 14 multi-domain datasets. That is, we have tabular, NLP, and vision domains in our benchmark. We evaluate 12 or more than 12 existing popular DA methods, which are based on sort of domain invariant representation learning, self-training, and test time adaptation. And we train sort of a lot of models to come to the conclusion that I'm soon going to present. Okay, and just to give a brief overview, we have sort of these multi-domain datasets, and I'll maybe illustrate with an example what do we mean by multi-domain with respect to, let's say, CIFAR 10. So let's go into that. So because in most of these datasets, we do not have any default label proportion shift, we simulate target label marginal shift by doing stratified sampling from Dirichlet distribution. And we keep the source label proportion fixed to the original source label proportion that was there in that multi-domain dataset. So and to simulate various degrees of these target proportion shift, we sample with different Dirichlet parameter alpha. So we sample our target label marginal from Dirichlet distribution with a controllable parameter alpha, where higher is the alpha, less severe is the shift. Or conversely, as alpha sort of decreases, the shift severity increases. And to demonstrate this with an example on CIFAR 10, we have these natural shifts in P of X given Y, which can be due to differences in image replication studies, which is CIFAR 10 V1 to CIFAR 10 V2, or due to common corruptions like frost, pixelate, saturate. And at the same time, for each of these pairs, we have target label marginal simulations which are of different severity. So as we move towards right in the bottom, the shift severity in target label proportion increases. And just to like highlight here, the orange bars are the target label proportion and the blue bars are source label proportion. And we can clearly see that the target label proportion is getting more and more skewed as we move towards the right. And we basically take a cross product, that is, for each target distribution from CIFAR 10 V2, CIFAR 10 C frost, and others, we have different severities of shift. So for example, in this setup, we'll have like 20 different target distributions for the source distribution, which is CIFAR 10 V1. Okay, and we evaluate different popular domain adaptation methods. I'll not go and describe each of these, but just for interested audience, I'm showing them here. Like these are the different popular heuristics in the literature that we evaluate in our benchmark. Okay, and to make sure about certain things with respect to fair and realistic evaluation, we re-implemented all of these methods with consistent design choices. We made sure that our model selection criterion is transparent. And basically what do we do is we select models based on source holdout performance, and we do not peek into target performance for any hyperparameter tuning. And we keep architectures and like pre-training details consistent across different methods. And by default, because we have seen sort of data augmentation helping, we default to using strong augmentations with like randog on vision datasets. Okay, so now I'll present sort of our results from running experiments with these different methods on our benchmark. But before going into the result, let me just first quickly explain this plot. So on the x-axis, as we move towards the right, the severity of label proportion shift is increasing. That is, we have fixed source distribution, and as we move towards right, the severity of shift is increasing in the sense that the label distribution is becoming more and more skewed. On y-axis, we plot relative performance of different methods with respect to a source-only model, a model that is only trained with which takes labeled source data and does not look at unlabeled target data. And in particular, y-axis is just the difference of performance that we get with one of these domain adaptation methods minus the performance of source-only model. And these bars, these bars are capture variances across different data sets in our benchmark. Because we have like these 560 different shifts, we also plot what is the variance among these different data sets. And the solid line presents the mean performance in these distributions. Okay, so we can clearly see that in this plot that as we are moving towards the right, the performance improvement that we get with these different domain adaptation methods decreases, and often it goes below 0, which shows that if you have severe label proportion shift, it may hurt you more if you tend to use some of these existing domain adaptation methods. And we show this failure is more widespread across different existing domain adaptation methods. And the trend for all of these methods is roughly the same. That is, when we do not have any label proportion shift, we see that these methods often help over not using unlabeled target data. But as the severity increases, severity of target label shift increases, these methods start hurting more as compared to a source-only baseline. Maybe I'll pause here if there's any question. Otherwise, I'll move on to discussing some of the solutions or like baseline methods that we introduce in our benchmark. Okay. Okay. So we showed in like previous slides, like just to give TLDR of like previous slide, we show that performance of these different DA methods sort of tends to falter when we have a label proportion shift. And in our, while this failure was known for like one of the existing method, which is based on like domain adversarial training, which is DAN, we show that this failure is not limited to those methods, but is more widespread to like even more recent methods like fixed match and 1010B and ADA. Okay, so to mitigate or to like make some of these problems a little less severe, we introduced two very simple general purpose corrections in form of a meta algorithm that we can plug in with any of these existing domain adaptation methods. So let me introduce these corrections. So the first correction is a simple resampling based correction in which at a high level, we balance our source data and pseudo balance our target data. And what do I mean by pseudo balance? Is that we take the model that we are training, let's say at iteration t or at epoch t, which is denoted by ft. So we take the model at that epoch t, pass our unlabeled target data, and get pseudo labels, which we denote by y hat t. Then we perform some form of class balance sampling by on labeled source data and this pseudo labeled target data. And then we repeat sort of one epoch or like one iteration of the domain adaptation algorithm of choice. So at a high level, zooming out, what we have done is we have pseudo balanced to either uniform or like source label proportion. We have pseudo balanced our target data to like source label proportion or like uniform label proportion. And then we iteratively sort of do this at each epoch till we get the final classifier. Okay. With resampling, our goal is that even if we get all the like our goal is to train this classifier on a mixture of balanced source and balanced target data in an ideal scenario. So in an ideal scenario, when all of our pseudo labels were, let's say, correct, the output or the outcome will be, we'll train sort of a classifier that is trained on like balanced source and balanced target data. However, this still leaves open the question of adapting my classifier F on original target label distribution, which is still not available. That is, we do not have access to our original target label proportions. And the next correction that I'll introduce will try to sort of adapt this classifier to original label proportion. That is the label proportion that we had before we resampled our target unlabeled data. And for that, I'll not go into the details of these methods, but there are existing black box methods that take in labeled source data, unlabeled target data, like labeled source and unlabeled validation target data, take some black box classifier and spit out one estimate of target label proportion. And we use these estimated target label proportions to simply reweight our classifier. That is, we reweight the softmax output of our classifier with these estimated label proportions. I can go into details of these methods after the talk if anyone is interested, but this is the high-level correction that we have in our work. Okay, now we show that by using these corrections, we mitigate and ameliorate, like more than like mitigate, we ameliorate, like we make these problems that arise due to like shifting label proportions less severe. That is, we can see here that, so we apply this correction incrementally. So none here is the plot that we have copied from previous slide, which is without any correction. And we incrementally add these corrections on top. So the green curve here is with resampling correction. The grayish curve here is with reweighting correction. And the red curve here is with resampling and reweighting correction. And we can clearly see that while the original method sort of falters when the severity in shift increases, this correction, when applied together, we avoid that faltering problem. Okay, and we show that this happens for almost all the existing popular DA methods. We have a lot more plots and like a lot more details in the paper, but I've included 3 representative methods in the slides here. And just to sort of present some aggregate results. So these plots here had y-axis, which was like relative improvement on top of like a source only classifier. We can perform some ranking of all these different methods that we have in our benchmark across all the distribution shifts that we have in our data set. And I have sort of aggregated them according to different multi-domain, like across different modalities, so vision, language, and tabular. And we see that almost often methods with our correction tend to outperform other methods and even like the source only model where we do not have these corrections. And this happens for almost all these, all the modalities. And again, like going a bit more into like these results, we show that simply involving these resampling and reweighting based corrections on the originally proposed DA methods often does better than some of the existing heuristics that people have proposed that specifically tackles the relaxed label shift problem. I can like discuss these results more if anyone has any questions with respect to any method, but yeah, I just want to like give a glimpse of the comparison with existing methods that were specifically proposed for relaxed label shift. Okay, I'll skip over these takeaways and maybe in light of time, I'll go to like concluding remarks. So we introduce RLS bench, which in some sense sort of provides sensitivity analysis to measure how robust some of these label shift estimation methods are under various perturbations of P of X given by distribution. And relative to like the benchmark driven DA literature, our benchmark sort of provides a more comprehensive and standard suite to run these empirical evaluations. And we believe that this is sort of going towards with these kinds of benchmarks, we are going one step closer towards the kind of diversity or like the sort of different problems that we may expect to encounter when we are deploying models in the wild. Because when we fundamentally have only access to unlabeled target data, there's no reason that the label proportions in my target data will match the label proportions in my source data. And we also have like sort of a word of caution, which is like, while these results are promising, given that this domain adaptation problem is sort of fundamentally underspecified, these benchmark results should be taken with like a grain of salt. And one should always think about like what are the problems that they are encountering and how maybe results of our benchmark would apply to their setup. And yeah, there are like some interesting future directions, which is like one of which I'm sort of currently pursuing is like, how would self-supervised methods like these contrastive learning methods would react or like would behave under similar proportion shift from like source to target. There are some interesting extensions to like open set problems where among with previously seen classes, we may have unseen classes in my target data. And we are trying to sort of theoretically characterize why label shift, like introduction of sort of label proportion shift breaks a lot of these existing methods. And yeah, like maybe why some of these corrections are like theoretically principled. So these are, I feel like, some of the interesting future directions that are worth exploring. And yeah, if you have any question, I'm happy to take them. We have our code and paper and everything sort of open source. So please feel free to refer them, or if there's any question, feel free to shoot me an email or ask them right now.
Right. Thanks a lot for the wonderful presentation, Saurabh. I think we can now take some questions if someone has some.
Hey, I had a question about your setting. In the beginning, when you were giving the archetype example of the medical data set, so you said like how between different hospitals, for example, like the way they get their data, the way they do their imaging could like sort of introduce a difference in P of Y.
X given Y.
X given Y. Would the other thing change? Like would P of Y given X also change when this?
So that's a good question. So for most of the non-separable problems, where we may expect that my covariate doesn't fully identify the label of interest, P of Y given X would also change. And most of these disease diagnosis problems, like for example, predicting disease from symptoms or like even mortality rates and stuff like that, most of these problems I think are non-separable in the sense that always symptoms are like not completely indicative of what is the exact disease.
Right.
So in those kinds of problems where like the setup is like the problem setting is not completely separable, label shift problems become very interesting. Because imagine like in COVID-19 scenario, earlier when we used to have the same symptoms of like common cold and flu, we used to say that, okay, it's maybe common cold. But as sort of the prevalence of COVID-19 increased, even when we started having like cough or like runny nose, we started thinking that, okay, maybe it's COVID-19. So as sort of these proportions change, the implication or like the underlying disease can also change for the same kinds of symptoms.
Right. Okay, got it. And I also had another question. So in your proposed method, like so you're saying in the target you're going to do like a pseudo
balancing,
pseudo balancing, right? So how does your sampling efficiency be affected by the pseudo balancing?
So sample efficiency. So there are some details in how we implement pseudo balancing, but what we basically do is we sample with replacement. So basically the sample efficiency is mostly guided by label source data that we have. And because we are sort of rebalancing to source label proportions, we don't see sample efficiency getting impacted by a lot.
Okay, got it. Right.
Yeah.
Okay, because you would be more concerned about sample efficiency in the source domain rather than
Target unlabeled
target.
data. Yeah.
Okay, makes
Yeah.
sense. Okay, got it. All right. Thank you.
Maybe I have just a application question. So maybe these methods, these benchmarks, and do you think this maybe in some ways applied to tackle the generalization problem in robotics?
Definitely. So yeah, so I have some like initial thoughts on that problem. So robotics often suffers this distribution shift problems. That is when you're trying to sort of explore, or like a policy is trying to sort of explore the distribution that we see in the wild can be very different from the distribution or like the policy or the data that it has seen sort of during training time.
Exactly.
Yeah. So I do believe that like a parallel here would be thinking about how, as the distribution is changing, how is sort of proportions of different actions that I may take changes, and we should think about like adapting to those. I've not worked in robotics a lot, so I'm not like I'm not very clear about what exactly or how exactly this would translate. But I have like some very high level thoughts on like how I think it may apply.
But it can definitely be applied, right?
Yeah. Like if you are thinking about like some discrete decision space, then I think this would definitely apply when when the target domain where you're deploying the model, we believe that the distribution of actions is very different, or it should be like, so for example, when we have a robot, let's say self-driving car, when it's trying to drive on straight roads versus trying to drive on a curvy road.
Yeah.
There, if we think about like the steering angle is one of the actions, then yeah, I think this would directly apply.
Yeah. All right. Thanks. I think Srini has a question. Yes, Srini.
Hey, I have a question. So like just a follow-up of what you said. So when we are dealing with some discrete like action space, right? Like how do you deal with like long tails in like a real world system? Like
That's
you mentioned about like the oversampling and class weighting, right? Does it address like all the issues that we encounter in real world? And what about like domain randomization? Do you think it's like a way to mitigate the oversampling, way to mitigate the bias, like in the dataset, like in the target dataset?
So okay, so let me answer your first question, and maybe I'll ask you to repeat your second question. So yeah, that's a great question. That is, how would these things pan out in like long tail problems? Currently, we are thinking mainly about skews in our target label distribution, and we have assumed that each class is decently represented in my source data. If I have these problems of like long tails in my source domain, then we will also need to incorporate some of the training techniques that people have developed for like specifically for long tail learning. And I think there are many different things that people have explored. But now if we have like a decent representation in source and the long tail problem is specifically in target, then yes, I do think that these methods alone would sort of you would start seeing some of the benefits of these methods alone. I don't know if that answers your first question.
Yeah.
You also had a second question?
Yeah,
the
can you
second
please?
question is like when you are like you mentioned about like label proportions, right, in the source and target distribution. What about like domain randomization, where we like induce like variability in our training data set to address that?
So I'm not specifically aware of like what do you mean by domain randomization, but do you mean that there's some form of like covariate support shift or like shifts in like covariate distribution among domains?
So basically in robotics, right? Basically, like we use domain randomization to help the model to handle variation and variation in real world. So basically, like we generate like a large number of like synthetic data sets by randomizing like different aspects. Like say for example,
I see. I think I got it. Okay, I got it. So
like,
this falls under like this problem of like domain generalization for like specifically like classification problems. And yes, these techniques would again apply when we have multiple different source domains. So if I project back your setup to like this classification, like multi-class classification problem, I would assume that I have multiple different source domains from which I have labeled data. And all of these source domains differ in some fashion. And the hope is that that factor of like we have sort of captured some variation, and those factors of variations would now transfer to maybe a previously unseen target domain, right? Like that's the hope of that's the hope from what we get with like domain randomization. So I would believe that if we have target unlabeled data, even in those setups, I do think that again, mitigating or like trying to adapt to like target label proportions would help. But now we would think about like problems or like methods that can incorporate label data from multiple source domains instead of like a single source domain.
Okay. Thanks.
Yeah, that was a great questions.
All right. So are there any more questions? If not, I think we can wrap it up here. So Saurabh, thanks again for the great talk. I think everyone enjoyed it. We will let you know once we prepare the video and the SoundCloud and Spotify so that you can maybe also reshare a bit on your channels.
Yeah, thank you for having me.
Yeah, I can quickly, maybe if you can stop sharing, I can introduce the next speaker and then we can close the session. Okay, so for the next talk, we will have Dan Grollman from +1 Robotics. And the talk is about a human-in-the-loop approach to parcel variability on 5th April. So see you guys there. Okay, so thanks again and have a wonderful rest of the PhD, and hopefully you figure out what's next.
Thank you. Yeah, thank you so much.
Thanks, Saurabh. It was nice meeting you today. Bye.
Yeah, likewise. Bye.